Hey, good morning, NV Hung. Did you have a question? I saw you raised your hand. Feel feel welcome to post in chat or speak out loud. No biggie. Alrighty. Well, oh, looks like someone left. Okay, they weren't interested. um, I'm gonna get started right now because we have a lot of material to cover. I was expecting a larger audience, maybe like 4 more people to show up. They might trickle in as we go, but for the sake of our own time, I'm just gonna continue. This meeting today will be recorded, and I'll be sending that out to you guys. So if you do miss something, you can always refer to the recording, or you can ask me questions later. This is a very laid back presentation, but I will be covering a lot of information. All right. So let's get into it. This is an introduction to PLCs in general, not just ours, but more a better understanding of PLCs, and then we'll dive into the specifics of our own PLCs. So if you don't know what a PLC stands for, it's a programmable logic controller. And then this is what Cimon education will look like towards the future. We're going to make presentations, little tech videos to help out and bring up the population on you know, getting into the whole automation field, just making it easy for everyone. So just a little bit about a brief introduction about our PLCs in general. We have the XP series for large projects, the CP series for moderate, and then we have the PLCS for small type. One second, let me admit this person in. Good morning, we've already started, just wanted to let you know. So in terms of Allen Bradley, XP series would be comparable to their control logics. Excuse me, CP series would be comparable to their compact logics, and then PLCS would be more so their micro logics. If you're like trying to find some type of a comparison, if you're familiar with some PLCs that are already on the market, that would be the comparisons to kind of look for. If we look at our XP series, we have larger memory, higher performance. This coincides with saying that it's like control logics, and then as we trickle down, we get smaller memory, lower performance, but we still retain that ability to be a effective PLC. It just depends on what your project is. So as we get to the PLCS, you can see that we still have the high-speed counter. We can still position, like controlling a servo. We can still communicate over serial Ethernet, DMP protocol, all of that. Hello, good morning. Just we've already started. If you only missed about the first like 5 minutes, you'll get the recording. No worries. All right, so then moving away from our specific PLCs, where can PLCs just be used? In general, they can be used in these categories here, so we can be measuring electricity, so voltage or amps. We can be using them for smart farms, agriculture, power plants, the same thing with electricity, water treatment, public transportation, and all in all, vehicles in general, so automotive or automotive and creating automotive vehicles, whatnot. So let's just jump into the basics of what a PLC is and why we would want to use a PLC versus some other examples out there. So by definition, a programmable logical controller has memory, it has I/O points that it talks to, it It provides arithmetic capabilities. It controls machines and processors. All in all, it's a CPU, but without the big screen, so you can actually see what's going on in the background. You would have to hook up into it and actually see what's going on. So a PLC is really good at doing that command that it was programmed to do, and it does it very well. And the reason that the PLC was invented or created was to replace what we see right here as a relay panel. So this was the nitty-gritty types of relays that were used to actually control machines back in the day, and actually some now still use this method. But as we see the time going on, we're starting to see less and less of this, and PLCs are starting to transition in more, and they're becoming a much more attractive product. So like as the next picture will provide, this is what happens when you incorporate a PLC into your woodworks. So you'll see it looks a lot cleaner. It would be easier to replace. As I get into the next slide, it'll be a compare and contrast for you. But ultimately, this picture looks a lot cleaner than the existing relay picture I just showed in the previous slide. So this would be a little bit of a compare and contrast of a relay versus a PLC. We do focus a lot on the cons of swapping to relay to PLC, or what you would experience if you stayed with just relay. This would be the cons. But I mean, there are some cons of having to use PLCs. One of them would be having to learn the coding, or having to be getting adjusted to new products, whatnot. There is a learning curve to PLCs. It doesn't just work straight out the gate, right? But as you become more exposed and more experienced with PLCs, it makes it more attractive as a product than sticking with relay products. Good morning. We've already started. You will be getting a recording of this session. Just wanted to let you know. So don't worry about what you've missed so far. So just touching base on where we can use this in applied areas, so we can use it for pollution, distribution, water supply, and sewage. We've already kind of touched base on this. I'm not going to go too much into detail. I just want to highlight some cool little areas that you could use PLCs in. So textile chemistry, food industry, the automotive industry, steel manufacturing, and then all in all, when you have your automated services set up, it will look something like this. Someone's having feedback. Hold on. I'm gonna have to mute you. I'm sorry, Peikung, that your mic is giving a little bit of feedback, I believe. Let me see if that is. Hello? Okay, yeah, it was that one. No? Hello? Hello? Okay, never mind, it was that one, sorry. So yeah, so if you guys have questions, just send a message in chat or raise your hand, whatnot. You can unmute yourself and ask me directly. I don't mind at all. But if your mic has feedback, I'm going to mute you for the time being. Just unmute your mic. It's in one of the settings where the toolbar pops up. You can just unmute yourself. So going back to this slide right here, this is what the automative lineup would look like. You have your sensors at the bottom. They collect all your data. They're performing certain tasks, or they're a servo, whatnot. And then ultimately they're talking to a PLC or an HMI, and then those two will communicate with each other, and then eventually they can send that information to a SCADA server. And that SCADA server can be accessed via a web server, via your phone, via another SCADA runtime. So there's a lot of shifting motion going on in the automotive field, which is allowing versatility with your automotive or your automative setup. It's letting you view your data easily. It's letting you change what's going on in the actual lineup itself without having to be there physically. It's really awesome stuff that we're encountering. And then on top of our product specifically, we do support Android and Apple for our app when it comes to the SCADA server or SCADA software. Just wanted to heads up on that. But moving away from this slide, we're going to jump back into the PLC hardware and software aspect. So for the hardware, you'll have a base component, which is called your chassis. This hosts all of your modules. You would just, you put them inside it, and then you screw them down, and then they become part of this one collective object. and then you'll have your power source, whether it be AC or DC, providing to the rest of the chassis. It'll be providing DC, but it can accept AC or DC. And then we have the CPU component, which is the brains of the outfit. It's doing all the processing, it's computing all the logic for you. And then we have our I/O special modules, which we'll cover over a list later. But just a little heads up, we have like things that can weigh, you can position, you can high speed count. All of these are tools that can help speed up or make your automotive process a lot easier. And then in regards to competitors, a lot of people have different software. Like Allen Bradley has two different softwares for their lineup of hardware. They have like Studio 5000 for control and compacts and guard logics. And then they have RS Logix 500, I think, for micro logics. So like they have different software. When it comes to our hardware and software, we only have one universal software called Cimon. So you can use that for the XP, the CP, or the PLCS series, and the future PLCs to come out. You'll be able to use it. It's universal, it's free, and also it is upgradable for free as well. So like if we come out with firmware upgrades in the future, you will get those and it will be of no charge. So a little bit about our CPU processing. When you first initiate the program, it will do an input refresh. It will check all of its inputs to see if they're on or off. It will execute the executions of the outputs, and then it will end the program. After it does that, it will commit a self-diagnosis, making sure that nothing's wrong, that if something is wrong, someone could be damaged or hurt. So we don't want to commit to this operation will cause an error. So someone potentially wouldn't be hurt, right? And then we have an output refresh that will basically reset the whole output because it's already been committed to in the program execution, and then we'll rinse and repeat this whole cycle over and over again. So we have two types of PLCs. We have the block type, which is for your very, very small projects. This is not expandable. It's for something that requires 8 digital input and 8 digital output. It has a processor already embedded, and then it has a power supply that just needs to be provided with an AC or DC current, and then it's good to go. It's just a little simple little block type PLC. But then down here we have the module type PLC, which is probably you're probably more familiar with, that you can expand upon. You can use analog, digital, you can use weighing, high-speed counter positioning, PID, all that fun stuff, redundancy. So that's more applicable when you look at the module type PLC versus the block type. When we're stepping back talking about our specific products here, we have the XP and the CP. We can look at their speed for processing, which we have 75 nanoseconds per program scan. And then we have 200 nanoseconds per program scan. So these are very quick speeds that these programs are being scanned at to commit to these operations. So they would be helpful if we did have a self-diagnosis little feature that we do have. So when we think about the I/O counts, we have a max of 8192 when it comes to the XP, and then a max of 1024 when we come to the CP series. This will be the same max for the PLCS, but you'll see that I say 384, and I'll go over that a little bit. But when we look at the program memory, we have 64K to 128K steps, and then we have 16 to 32K steps. And what I mean by steps, if I jump into the Cimon software here and I just open up a basic project of mine, let's see, I think it might be this one. Can we open this one? Okay. So as we look here, you'll see a number 4 or 6 or 12. These numbers represent the number of steps that came prior to this rung. So prior to rung 4 here, 12 steps were utilized up here. So that's what I refer to when I'm talking about steps for the program memory. Otherwise, the physical data memory of the PLC is 7 megabytes, and then we step into the kilobyte range when we step down to the CP series. And then the rest of the specs are here. There will be a bigger spec sheet to look at. There's the catalog and manuals that you can look at as well. If you need help finding those, just let me know. When we step down to the PLC, the block, and the module type, you'll see that our I/O count went down significantly, but the I/O max is actually still 1024. We do have an expansion module that is coming out relatively soon, so this will increase the I/O count. But As a physical limitation standpoint, it's 384 because the PLCS can only expand up to 12 modules as of right now. In the near future, within a month or two, we'll be able to expand and up to at least 16 bases, and you'll have up to 1024 IO count for that. But I would still recommend only using the PLCS for a small time project. It's comparable to the micrologics for those that came in a little bit late. So we have the data memory similar to that of a CP series, and then we have the CPU, the power, IO, all as one module. It sounds similar. It's kind of like the block PLC, but with the whole expansion capability. Internally, it comes with Ethernet, serial, RS-232 and 422, 485, those type of serial communications. The loader port is the USB Mini B, and it has an SD card slot. We'll go over more of the anatomy in a future slide. Just wanted to highlight some of those. Here's the power supply for the CP or the XP series. So as we have here, plus 15 and minus 15 will be for the analog modules. Any power supply that you get typically will have the plus 15, minus 15. We are not like recommending getting the SPA power supply anymore. We still provide it, but I recommend staying over here in this territory. The caveat to this territory would be the SPR. This is a redundancy only power supply, meaning you wouldn't want to use it with a normal base, and vice versa. You wouldn't want to use a normal base with the redundancy base. You could damage or hurt the hardware itself, and or you could damage the base, meaning the hardware. Just wanted to cover that little bit real quick. But typically you'll be staying over here with these four, and the difference between these two would just be the input voltage, honestly. So SPC would be alternating current, and then SP2B and SPW would be your DC current types of input. Overall, this is the power supply for the CP or the XP. When you touch base with the PLCS, you just need to provide a 12 to a 24 power DC current. So it's a little bit different in terms of the XP and CP. So here's some of the anatomy and the specs of the PLCS. So on the front side, you'll see we have an SD card, the USB Mini B port right here, and then we have the mode switch up here. 16 digital input and output. This can be 8 digital input and output, but that would be the relay module. This right here is sync or source, so you have to specify which one you want. Our inputs can accept sync source, doesn't matter. So just the only thing that would be changing would be the digital output scheme, honestly. We have an Ethernet port down here that's 10 by 100. We have our power input here, so 12 to 24 volts direct current. And then we have the serial port. The first 3 is dedicated to RS-232. Then the last 3 are dedicated to the 485, 422, as you see over here. It doesn't say 422, but they're both isolated on these 3 ports down here. You'd use a green block connector, and then you could reference our manual, or I could help you set up the direct current or the direct communication between the devices. So we have D plus, D minus, and then a grounding little rod for the communication, and then we have transfer, receive, and then a grounding rod for the communication when we talk about RS-232. The rest of the specs here. A little something that's notable about the PLCS is that when it comes to the Ethernet port, it can accept Modbus TCP slave, but it cannot do Modbus TCP master. You would need an Ethernet card that's dedicated to that, meaning. And then on top of that, it provides serial Modbus and master and slave. So if we look right here, it can do Modbus, master, and slave through serial, but just slave through Ethernet. You would need the dedicated Ethernet module, just to reiterate that point, if you want to do Modbus master with the PLCS. So jumping back into the XP and the CP, this is a little bit of a comparator slide. For your reference, I will be giving this presentation out to each one of you guys so you can look at this and kind of see the comparison. I'm not going to touch too much into this, but just a little highlight or just a reiteration that the XP series is the superior series to the CP. So in terms of comparing, you would always think that the XP is going to be better than the CP. All the specs are essentially going to be better. So when we look at the special modules, I know I said I was going to touch base on this, so here we go. We have some AD modules, we have DA. So these AD and DA modules is analog to digital, meaning you're turning your physical values into digital values that can be computed or in turn be data throughputed into like the SCADA or the HMI. And then this can be recorded via amps, or it can be recorded voltage. I meant current, milliamps, but all in all, that's what I'm talking about when I'm talking about analog to digital. Then we have digital to analog, the same stuff, but instead it's taking a digital value and then shooting out an analog value to your physical machines. And then we have RTD, we have TC and thermistor. These might sound familiar as these are temperature modules. So these would be in reference maybe to PID or just recording temperature in general. We have load cell modules. So this would be more so for weighing things. You can weigh a variety of things. We have very flexible types of load cell modules. We have a high-speed counter module. So if you need to count up to 250,000 pulses per second, we could accommodate that feature. We have data logging modules. We have the positioning modules is becoming very famous. So like controlling servos is becoming a more popular trend these days. And then we are staying current with all the communication out there. So we have adopted the OPC UA server module. I don't know if many of you have heard about it, but OPC UA is kind of new in the WordWorks, and we are supporting that in terms of communication. There are other open source communications like Modbus. A lot of people are still stuck on Modbus. They don't like doing all that programming. I understand that, but all in all, Modbus is pretty easy. But we do support Modbus, OPC UA, DMP3 protocol, 3.0 protocol, all those types of protocols. So when we look at a special module, as we just mentioned, the CPU is going to be communicating with that special module. The special modules do not have their own processor. They just store memory, and then they have to be retrieved via the CPU module. So then this is where you would use a from to command. So the CPU sends a command to the special module saying, I need memory slot 11. So that would be buffer memory or user programmer memory number 11 using a from command. But if you needed, see these special modules, they also commit to certain actions with their IO area. So if you need the special module to commit to a certain action, you could actually send information to store in its memory, and then it will commit to that action with its IO area. We'll go in better detail with future slides. This is just a little preface to how special modules work. So when you look at the IO area, you have X for input, Y for output, and then they're used simultaneously. So every special module is essentially allocated 1 word of X data and 1 word of Y data. So that is 16 bits for X and 16 bits for Y. And that is just by default. There are exceptions, and we will cover those exceptions. For user memory area, this is also referred to as buffer memory area. So this is where the data is stored inside the module, and it's retrieved using from or to. We do support a lot of syntax, so we support instruction list. So when you make your ladder diagram, you can convert it to instruction list. Even if you don't know how to use instruction list, you could just do conversion to see what it looks like if you feel like it's comfortable for you. A lot of the time, it will not be comfortable because it's not used very often, as we state in this slide here, but we do support it in case you do want to use it. Ladder diagram tends to be the most popular choice of everyone, because it uses relay logic, which is the PLC was replacing in the first place. So here's the ladder diagram slide. This is kind of what ours looks like. It should look similar in some fashion to other competitors because ladder diagrams don't really change in essence. You have your inputs on your left sides, and then you have your executions on your right side, your outputs. If the left-sided conditions are true, then the right side will commit to its certain actions. So this is what we call relay logic. We have sequential function chart, which is a different type of logic that incorporates ladder diagram, but all in all, it's a different type of logic itself, the way that the CPU processes the information. Now, the way to access this, it's because it's not intuitive right at the gate. So by default, your screen will look something like this. It won't have the program here, but the toolbar up here will look like this. To get the sequential function chart, you have to right-click here, make a new program. At the bottom right, you'll see a sequential function chart program. You can click that, press OK, and then, okay. So then you'll get something that looks like this, and then you can start messing around here, building up your whole tree diagram. And then on the right side, you'll see per condition, you have ladder diagram logic over here on the right side. Now you'll be asking, well, where's the operations for these? These are committed, and by default, they're not set up because typically people won't use this program. To retrieve them, you can right click here on the toolbar, and then you can just click on FSC transition menu and FSC step menu. And then both of those options will pop up, and then you'll be able to start committing to your program that you chose with FSC. And then that was FSC. Let's talk about function block. This is a part of ladder logic. When we have function block data, this is utilized to make your programming simpler. So if you have something that's a long list of coding and you just want to do it in one simple block, you can. We also do have embedded function blocks. So at the bottom left here, we have a library of function blocks that you can utilize. And straight out the gate, I do want to cover something. Let me delete this real quick. So delete program project. I want to make a new program, scan. So the way to make a basic scan, I'm going to walk you through it real quick. The last rung, it does have a program end. You would want to type in end and then have another rung that commits to that end feature. And then I want to do some bit bit comparators, because I can't do word comparators with the given parameters. So if I do application instruction equal, so if I wanted to compare 2 bits, so if I did x11 and x12, because these are 2 bits, I'll go into why they're bits later, but I want to show you that this is not possible. So it gives me an error saying I can't compare bits because this operator is only being used for words. So if I wanted to compare bits, I would come over here and then pick the simple examine if closed operation and do that twice for x12. And then I'll do it if they're false as well. So see how that was kind of like a lot of work. It wasn't a lot of work, but this is just a minor example of what I'm trying to say. I had to do some processes to actually do bit comparison, whereas if I made a function block that was dedicated to this, I would only have to input 2 little bits every single time and I'd be good to go. So right here it's comparing if x11 and x12 are both on or if they're both off, and if they're both on, it will commit to the action. If they're both off, it will commit to the action. And then I can make a function block that literally embeds this function for myself if I want to. So that's a little bit about function block diagrams. Coming soon in the future, when we have our Linux-based PLCs, we will have structured text. So this will kind of remove the whole need for relay logic. You can actually type in the logic that you want to use. So you can declare, as you see right here, we're declaring our variables here and we're ending our variable declaration. And then we go into our logic. So if switch 1 is true, then lamp 1 will be true. So if switch is on, turn the lamp on, else it will stay off. So eventually we will be at this, and that will be when we have our UP series and our PLCS Pro, which will be coming out later in this year, which will be our Linux-based type PLCs. So that was a little bit about our syntax, a little bit about the PLCs themselves, and a little bit about the internal compartments of the Cimon software. Any questions before I move into part 2? Feel free to write in the chat or speak out. You can unmute yourself if you want.
Christian, can these PLCs control like field bus devices from other vendors?
Yes, field bus is something that we support. So if I go over here into new program, we have a field bus protocol right here actually, but it's not supported by the PLCS. But what I can recommend is you can use like an X panel HMI, which I'll be covering over on tomorrow. I'll be covering the X panel tomorrow. And then that's typically our open source connector. So our X panel has a lot of native drivers, whereas our Cimon software typically just talks over Modbus. It could talk over our own protocol, which you would talk to the HMI. It can talk to DMP 3 or DMP 3.0 field bus, but not the PLCS. And then it can do OPC UA as well. So not totally limited, but we do have a lot of open source protocols when we talk about the PLCS or the PLC in general. And then when we move shift gears to the HMI and the SCADA, that's when we get into the true open source protocol utilization. So in essence, yes, you would be able to use these PLCs to talk to field bus devices on your location. Is that good? Okay, moving on. Going into part 2, let's do a little bit of the PLC introduction. So if you're not familiar with data registers, now is a good time to learn. A bit is a 0 or a 1. So this is the bare minimum for data registers. A bit, a 0 or a 1. Do I want to turn the lamp on? Do I want to turn the lamp off? Now, a not so common term, but something that'd be nice to know, is a nibble. A nibble is 4 bits, so it has 16 possible expressions. And then when we get into the more familiar terms like a byte is 8 bits. When someone says a word, they're referring to 16 bits. And then when someone's referring to a double word or a double integer, they're referring to 32 bits. And then these are the possible outcomes on the right over here for you. As you can see, when we get into double word territory, the number gets it gets really large. So a little bit about our data registers for Cimon itself. This might be familiar with some other competitors. When you look at Allen Bradley, they use I and O. When you look at Siemens, they use I and Q. And then when you look at like Mitsubishi, they might be using X and Y. There's some competitors that they're very similar to ours. You know, so every place kind of has their own niche little device area registers. So for us, X and Y is input and output. These are your bit. They can also be word. M is a virtual memory storage. I would use this for like storing your memory bits. K is for latching. And these aren't necessarily, they don't have to be used in that fashion, but I would recommend using them in these orders because they're committed to those operations for the sake of that reason. So K is identical to the M area, but it's supported for latch. So I would leave K for latching. L is similar to the M in case you run out of M. I would believe that you wouldn't run out of M bits and M words to use, but if you do, L is there for a backup. F, I would stay away from completely as these are internal bits that are read-only, so don't try to, you wouldn't try to program these bits or words. They're more so there for your use, and I'll cover some more of the F bits and F words later, but we have like counters in there. It'll be able to tell you if your power supply is dying. There's status checkers, indicators, and embedded functions within the F device area or your data register area. T and C would be for timer and counter respectively. S is for step control relay. When we want a word or a double word register, we will move to the D and Z range. So D and Z would be for your analog area, your 16-bit, 32-bit read and write areas. And then for R, that would be your index register. These are a little bit about the maxes that each CPU could handle in terms of its device area registers. So as we go from left to right, you can see that the number is trending downward. So is coinciding with what we said earlier, that the XP is for larger products or larger projects, excuse me, CP for moderate, and then as we step down to the PLCS moderate but small as well, I would recommend using PLC for small. Do not try to run a PLCS for the project that a CP would be required for. And then this has been discontinued, but we still do support, and we will always support our legacy devices because these are still floating around in the world because they're there. But typically these have been transitioned towards the CM3 series. We do still offer the block type, it's just under a different name. So I want to talk about our memory allocation in detail. So what the difference between hexadecimal and then the word version. So like on the left here, we'll see that we have X, Y, M, K, L, F. These are our bit registers, but they can also be used as a word. So I'll get into that a little bit, but the last bit the last placeholder for the whole register is hexadecimal. It may look like a decimal, so like down here it's a 0, but this is still a hexadecimal. M120 refers to the word, M120 or the 121st word, or it refers to the 121st word bit 0. So it could have two meanings. You would have to notate that in your logic explicitly. So for example, I'll go back to our scan over here. If I type in M120 here, this is M120 the bit. And then if I type in M120 the word, so if I'm doing like an equal M120 and then M130, these are the actual words right here. These are not to be confused. And then I'll show you what that looks like on the data register side. So if I go to connect option, and I go to simulator, so another little nice part about our software is you don't actually have to have the physical hardware to communicate with it first off, because it will take on the IP address of either your personal computer, or you can use the IP address that your computer is being assigned from your router or whatever, however you're assigning your IP addresses. So I'm going to go ahead and connect to the simulator. I just want to show you the memory register real quick. So if I look here, when I'm talking about M120, M120 is actually this right here, so the 13th word. So 120 could refer to the bit itself, or it could refer to this whole word. So this, if I type in right here, the address is 120. So this is the 13th word. So 1, 2, 3, 4, and it will highlight the respective bits that make 1, 2, 3, 4 possible. So if I turn this back to 0, or I can activate bit 120 here. And then this will be, those are two different uses of M120, but both meaning separate things. Hope that makes sense. As I step further in the direction of like hitting 10, because once you go from 9 to 10, you're hitting hexadecimal. So it goes A, B, C, D, E, F, right? F meaning 15, but the 16th bit because we start at the 0 bit. Also, you can rearrange the data. If you're used to seeing it from right to left, you can just do descending bit up here if it's better on your eyes. But typically by default, it's ascending bit. And then on the right side here, you'll see our word registers. We will not see any hexadecimal in the register at all. It will only ever be decimal verbiage because we don't actually talk to the direct bits when we do the word devices. So these will be our T, C, D, and Z registers, so different from these registers over here. So when we talk about our chassis, so we're referring to the XP and the CP series here. The PLCS does not need a chassis. It is it's expandable very easily on its own. It just snaps onto the right side and then it clips in on the top and the bottom. Actually, on the previous slide, on the anatomy slide, if you looked on the right side, there was on the top right of the right side, there was a connector, and then you will clamp the module in line there and then snap the two white little latches, and it will lock the IO module in place. But in regards to the XP and the CP series, you will have a base in the background that you need to screw the IO devices into to securely mount them. And it will look something like this. I want to just notice one fact with our bases. When we say 3-slot base, we actually mean 3-slot base. That means that you can use 3 IO cards. Some competitors, when they say 3-slot base, they include their CPU in that count, or they include the power. So notice that the CPU and the power are not included when I say 1, 2, 3 for 3-slot, and that works all the way up to the 12-slot. We get the full number disclosure here. And the same thing when we go for redundancy. The redundancies are the two power supplies for your redundancy. The power supply monitoring module and the CPU do not get counted towards this number right here. So this 5 is referring to the IO module. So 1, 2, 3, 4, 5. And the same thing as we step down to 10. So I talked a little bit about this earlier on the slide, that each IO card by default is allocated 1 word of X and 1 word of Y. So that is 16 bits of X and 16 bits of Y. Excuse me. As you step up to a 32-point module, so this is referring to our digital inputs and outputs, because every other module besides digital input and output will be allocated only 1 word of each. When we step up to 32 bits, we'll get 2 words of each, because that makes sense, right? Because we have 32 bits, so we need 2 words to allocate for that. And the same thing comes for our Y when we have the, like when we have a 64-bit, sorry, I was speaking about Y, but when we have like a 64-bit module, then you need 4 words because that's 4 words of 16 bits. And I'll showcase that on the Cimon simulator real quick. So if I exit that, let's disconnect from here. Let's go to reserved IO. It's a really nice showcase tool. So 12 slots. If I go digital input, 0 points, digital input and output, 16, and then 32, and then 64. I'm going to press OK. And then we can see that the chassis over here that automatically detects what modules you're using physically, honestly. It's pretty cool. It will allocate the data properly, and as we can see, the first module in line is the CPU. And the CPU is a 32-point module, so as you can see, it's allocated 2 words. So when I say 2 words, it looks like it's only jumping up 20, but that's actually 2 words. So 1 and then 2, because this, and again, this is in hexadecimal. So 2 words here. If I do 0 points, so maybe like a dummy module or something, then we would just allocate 0 data memory to that. Then when we step down to the 16 points, so the default IO card, you get 1 word of X and 1 word of I for that module. When we step up to the 32 point, you go back up to those 2 words. So from 30 to 50, that's 2 words. And then from 32 to 64, we'll jump up 4 because, or we'll jump up 2 more because we're adding on 2 more words. So in altogether, we'll have 4 words of X and 4 words of Y for our 64-point module. So hopefully that makes sense. When we talk about expansions and address assignment, the only thing I really want to cover from this slide is when you get your expansion module, you will notate which expansion it is with a little rotary little feature here. You declare what expansion it is in line, and the fact that you would only want to use, say you had expansion E, so that would be 15. You would only want to use this with in spot of expansion 15. So you would not want to use this like at expansion location 3 or 2, just making sure everything is in numerical order. So like you would want 1, 2, 3, 4, 5, 6, all the way up to 16, because the max is 16 for expansion of XP and the CP series, soon to be for the PLCS when we finalize our expansion module there, be a remote IO. But for right now, it's just the XP and the CP series. So when we talk about CPU redundancy, this is 2 CPUs side by side, one that will take over in case the other one fails. So some might be calling this master and slave, some might call this primary, secondary. Whatever term you've heard, this is the term for CPU redundancy in general. So if one fails, the other one will take over. And then they're both communicating synchronously, talking to the IO counts. And then down here, we'll see that this is power redundancy as well for the IO cards. This is like a typical setup if you're going to do redundancy in general. So as you can see for the power redundancy, there's 2 powers, and then there's a module in the middle that is actually monitoring both of them to make sure that they're both operating properly. So that's it for part 2. Any questions before I move on to part 3? Alrighty then, I'm going to move into part 3. This is the Cimon program structure. Now we're going to actually talk about the software. So when you get into the software, you'll have a blank canvas, and I'll walk you through what I kind of see when I open it up. So I'm going to close my project. I'm not going to make any saves. So when I open up Cimon, I get something like this. So I'll go to File up here, New Project, pick my PLC type. So I'm going to be choosing the PLCS for terms of this demo today. I'll click on Next. I can name it whatever I want. By default, it's going to name it by the date. So it's the 15th of June today, and it's 8:42 for me. So it names it by the time and then the date. And it will store it to your Cimon folder in your local drive. I recommend keeping the project folder the default path, because if you're going to be using, all the Cimon products utilize the same directory in a sense. They just split it up by a different software, and all your data kind of just stays in one little nice spot. So I don't recommend branching out your projects into different spots unless you feel very comfortable doing that. So after I make this, I press OK, and then I get something like this that pops up. This might not be here on the right side, but you'll see like program on the left side. So if you right click on program, or if you go to file, you can make a new program this way as well. But I right click, I click new program. To get started, you would want to press scan. Name your program name if you want to. The ID right here is this number, so the ID will change the program name. I recommend keeping them the same in terms of just because you will try to reference your program name sometimes when you're doing a project. So just, and it's easy for troubleshooting purposes as well. So I'm going to press OK, bring this up. To get your project started, you can either use the hotkeys. So I use hotkeys. Control L will create a new rung for you, or you can right click and then you can insert row. So we say row instead of rung, but they both mean the same thing. So Control L will create that row, and then Control R will delete that row. And if you're familiar with Allen Bradley, it's the reverse, because Allen Bradley's Control R actually makes the rung. Anyway, after I make my rung, you're going to want to put in an end instruction, because this is telling it to end this program right here, to end this scan, and then go on to the next program in line. As we can see that this is a program end indefinitely, so there's 2 ends per program. The project will not run accordingly if you do not have this end instruction. So we can put our logic here. We can start building up our canvas and committing to certain operations this way. It's very fun stuff. So if we want to create a password for our project, we can. It's here in security settings. When you make your project, click on security settings. You can put in your name, or you can put in the password itself. The only caveat to this is we cannot reset your password for you. So when you do your password, I recommend writing it down or creating a backup of your project. You can always make a project, go back and put passwords on it later. You don't have to do it you don't have to do it straight out the gate. So if you want to create a backup for yourself only that you have, then put a password on a public version of the project, you can. I don't know why you would do that, but the availability is there, and I just wanted to let you know that if you have trouble resetting your password, or you messed up your password, we can't help you reset that in the future. So a little bit about our scans. We went over the basic scan. It's a single process that repeats every time that the PLC is scanning and it finishes another program. So some people might know about subroutines, like being able to jump onto another scan in the middle of a program and then come back to the original scan to keep going with that logic. So that's what in our logic, that would be called a subroutine. You wouldn't want to use a scan to try to target another scan that won't work. So when you use the subroutine, you'll use an eCall instruction, which will target that other scan, and then it will come back to the normal scan after it's done. So that's a little bit of a familiar trait from other competitors, but ours is called subroutine. We have this other feature called periodic interrupts. So if you want something to occur from every 10 to 60 seconds or 60,000 milliseconds, you can program it to do that. So in that fashion that, oh, I want every minute for X, Y, and Z to happen. Well, you can use that. You can do that incorporating a periodic interrupt. When I talk about cold initialization, this is what happens. It's like you just booted up your CPU, you're writing in analog values, what have you, into your sensors and other devices. Before everything gets warmed up and started, you're writing in values to certain sensors and devices before the PLC actually starts committing to its scans. So this would be an initialization cold. So it programs a bunch of numbers before it actually starts scanning all the programs within the PLC. Then on the opposite side of that, we have initialization hot. So this would be used for a momentary blackout. The only caveat to a hot initialization is you have to be able to predict how long the blackout is. So if it's something that you're controlling, that will be easy to be able to predict, right? So if you're like, I want to shut the power off for 2 minutes, well, you would write that program in your PLC telling it that, oh, in the case of X, Y, and Z happen, or in case of a momentary blackout happening for 3 minutes, store this data on the side, and then shoot it back into the scan program after that. If you happen to not be able to predict the blackout properly, you will lose all that data because internally it is waiting until that time limit to actually send the data back into the scan program. So it's a little bit of a double-edged sword. So it's keeping your volatile memory handy, but it will only keep it handy for so long, but something that you yourself have to declare how long you want to keep it volatile for. It can't detect when the power comes back to your plant. You would have to tell, oh, the power is going to come back in like 60 seconds, a minute. Something relatively same with all other competitors. We have a run, remote, stop switch. So you can run remote, you can stop remote for programming different features. When you go into the PLCS, there will only be two switches. It'll be run or stop. Because it's a smaller PLC, it doesn't really need that program feature. And another thing to talk about with our hardware is you can actually program the PLCs while they're online. So it's a really nice little feature. When I come over here, this little mining tool right here, when I go online, I'll showcase that later, but I can actually online edit, and then when I'm done making my edit, I can come over here and then download that edit. Now there are limitations because certain things could be harmful. You could hurt someone after you do an online edit. So there are very small limitations to what online edits you can actually do. When we talk about connect options, we're going to be dealing with simulator today, as we've talked about already, but the top three, I would ignore the bottom two left. I mean, if you do use those, all the more power to you, but we won't be covering those in today's lesson. The top three, we have Ethernet. So it's something that would be set up after you have already connected to your PLC once. So either via USB or serial. And then you would program the Ethernet IP to it once you've connected and established communication. The USB is a USB to USB mini B, not a mini A or a mini C, it's a mini B. And then the serial communication, it supports RS-232, 485, and 422. Excuse me. And then we have the simulator today, or a simulator that I'll be covering today in terms of communication. So when you want to download a project onto your PLC, you're ready to get going, I recommend either using download, so PC to PLC. You won't be able to monitor your device, but if you're in a hurry or you already know something's going to work, you can just download it that way. If you want to monitor what you're going on, if you look up here just a little bit higher, it says link, download, and monitor. So this essentially commits to the download, but it makes sure that you had correct communication, and you'll be able to see what your actual registers are doing in real time. So that's really nice, a little nice feature that we will be utilizing with the simulator today. So you'll get some exposure to that. When I want to look at the PLC status, so this is more for troubleshooting or to check the features of your PLC in terms of firmware and other real-time clock features. So we'll see that the firmware or the OS version is right here. This is upgradable for free, and you can, unlike other competitors, you can revert in OS version. So I know with like Allen Bradley, if you go up too high in revision, that you can't step back down actually, and you just ruin that hardware and you'll have to buy a new piece of equipment. With ours, you can step up or step down freely with your own whim. Then you'll see that this is where you would actually set up your real-time clock. So you can set the PLC time manually, or you could set it to speak to your PC, and then it will store that information indefinitely. As you can see right here, there's an error message. So this would occur for if you're having an issue with your PLC, like an error code happens, it would come up here. You'd be able to see that. You can either diagnose it yourself by looking at the help manual, or you can send us that code because we always do provide free technical support, and then we can investigate that for you as well. And then you'll see the MAC address down here, and then how long a scan time lasts, like what was the last scan, what's the minimum, what's the max scan for the whole scan, not just a program. So there's multiple programs within one scan, there could be. So when we start setting up the ladder logic, these are the little commands that we're going to be using. You don't have to get adjusted to the hotkeys. I don't even use the hotkeys, but they're there in case you do want to use them. So if we want to draw a horizontal line, you can use F2. If you want to draw a vertical line, Shift F2, or the little button right here. So these buttons can be found right here. This is what I'm referring to. They're on your toolbar by default. So I'm going to go ahead and get rid of my FSC part of the toolbar. So by default, they're right here to mess around with. And we have our examine if closed, examine if open. So normally open contact, normally closed contact. We have our positive and negative transitions. So for those of you not familiar with what a positive and negative transition, if you're familiar with what a one-shot is, this is typically what a one-shot is. So when an F7 or this button right here becomes lit or turns to a 1, it will execute the command on the right side, the output, for one scan only, because that is what a positive transition means. It's a one-shot. And likewise, we have the negative transition. So when it goes from 1 to 0, it will activate the right side, the output, for one scan only. And then down here, you'll see that we have our coil, F9. So this is our digital output. So typically this is a Y. You can use it as an M or other bit as well. We are hitting the 9 o'clock mark soon. We'll be taking a break at 9 o'clock for about 2 minutes, and then we'll come back so you can like stretch your legs, stretch your mind, all that fun stuff. If you have questions, you can also post that in the chat. You'll see that this is our function block little button, Shift F9. Not so commonly used, but if you want to, this is where it's at. F10, very common, has all of our instructions inside it, like add, divide, multiply, block comparison, all the cool little features. If you go here, you'll see a library of instructions for you to go through. So if I want to see all the commands that relate to output, they'll be on the right side. And there's a tooltip right here as well that will help guide you through what the instruction actually is committing to. And if you need more help, you can always click on help. It'll take you to the help manual, and it'll give a more in detail. It'll give a detailed instruction on how to use that command. So let's cover this slide, and then let's cover the next two slides actually. So we'll cover the next two slides. I'll just walk you through what basic ladder logic this is. So in the top part, we have a normally open contact, so meaning examine if closed. So if this becomes a 1, it will commit to the right side. So when F90 becomes 1, Y20 over here will become 1 as well. It will become energized. So we call this energized output. Also, since it's on the same rung 4, row 4, it will also commit to the double word move. So D move stands for double word move, meaning it will take D0 and D1 and move them respectively into D10 and D11. So I'm going to show that on the memory monitor real quick. So if I go ahead and connect, I don't think it will let me. Go ahead and save these. So if I go to D device right here. So when I talk about double word, and remember we're in the D registers, so we're no longer talking about hexadecimal. It stops at 9 right here. So each one of these registers right here are a word themselves. So when I talk about a double word move, I'm taking D0 and D1, and then I was going to move them down to here. So D10 and D11. So this moves here, and then this moves here. So that's what we call a double word move. When we have a B contact down here, we have normally closed contact, so meaning that this is always on when it's a 0, and when it becomes a 1, it will turn off. So this is energizing the right side when it's a 0. So straight up the get-go, it's a timer. A timer is always going to be off at the start of it because it hasn't actually counted anything yet, and since it's so high in the program, it hasn't committed to anything until it gets down here. But this is a 0 straight out the gate, so therefore it is energizing the right side. It is increasing D1, and D1 was our word register. So for how long T0 is a 0, it will be increasing D1 by 1 every scan until it becomes a 1 itself. Moving down. We have F94, so this is a one-shot, so a positive transition. We need to remember that F94, when it goes from 0 to 1, for one scan, it will power on L00, and then after that scan, L00 will unpower itself because it's unless F94 turns off and turns back on again, and then it will only power L00 for one scan again. When M00 goes from 1 to 0, one scan, it will power L00. And then after that scan, L00 will become unpowered. When we look at 35, or when we look at row 16, 35 steps have been committed up until here. When L00 goes from 1 to 0 for one scan, it will count up to 3. So this is a counter up. We'll cover this later. I just wanted to kind of showcase this real quick. CO is counting up to 3, so 0, 1, 2, 3. And once C0 has counted to 3, it will fire itself. It will become a 1 itself. And this is read-only data. This is something that you can't really change internally. And then K00, when it's turned to a 1, it will reset the count. So this second part of the parameters is just resetting the counter. So it will bring the counter from whatever number it was at to 0. And then when C0 becomes 3, or count it, when this function has counted up to 3, C0 will ignite. It will become a 1. Typically, what people do to reset counters is they will make the variable that is counting up to be the reset. So people will put like a C0 right here, and once you've hit 3, it will energize down here, but it will also reset the counter for you as well. When C0 has been powered, it will turn the timer on and it will start counting to 100 ticks. So T0 is counting 1 tick per 100 milliseconds. So 100 milliseconds times 100, that would be 1,000 or 10,000. So that would put us at 10 seconds. So after 10 seconds, this will fire. This will energize itself, and T0 will become a 1. Well, we talked about T0 before. So when T0 becomes a 1, this stops executing, and then D1 would stop increasing. So that's just a little bit about this slide and a little bit about the ladder logic if you haven't been truly exposed to it yet. And then at the end, you'll see that the program ends. So let's go over this slide real quick, and then we'll take a short break. So if we go to view, we have variable window. Variable window will let us look at what variables we've been using. We can give them aliases. We can also do fast programming this way. So what I mean by that is when I'm going to disconnect real quick. I go to view, then I go to variable window, this pops up. This is the F words, we'll go over them later, but I'm going to go over to the X bit, show all the variables. Now, like in Excel, if I type in red1, in Excel, you can drag this down and it will auto-populate with the highest number next to it. So when you click on the cell, shift and then left click and then drag down, and then it will populate with the number in line. So this will make for faster programming if you want to give your data registers different names, what have you. This helps with troubleshooting later on, in case you need to show this program to someone else and you're not there to tell them. Correct naming of your registers can help other people troubleshoot your program when you're not there, or just in general. It's really nice stuff for future reference. And then variable would be the alias to that variable or to the data register. So if I name this blue1, wherever I type in blue1 on my program, it will populate with the data register X00. So that's just a little bit about the variable window, how you use it. You can transport from Excel. So I can copy the, oops, sorry. Okay. So I can copy this, I can go to Excel. And then just paste that, and vice versa. You can do the same thing in Excel. If I do green 1, and then drag this down right here, I can copy that. Let's go to Y bit, go here, and then it'll paste right into the variable editor. So it makes it very easy when you're trying to like program your logic very quickly with different tags. So you can just jump back and forth between Excel, or you can stay within the Cimon software itself. So let's take a break right here, and then I'll see you guys in, let's see, 2 more minutes. We'll reconvene at 4 after. Just go ahead and stretch your legs, your mind, what have you. Post questions in the chat if you want. Alrighty, doesn't look like there's any questions. I didn't hear anyone. I was able to stretch my legs. Thank you guys. I'm gonna jump back into it if anyone doesn't have any questions though. I'll just wait a couple seconds. Alright, well, I'm gonna jump right back into it. So we just left off at how to edit the variable window, talking about Excel, being able to move back and forth between the devices. So let's talk about another feature within Cimon. We have the find and replace option. So if you mess up with your program and you accidentally used X12 too many times and it was actually supposed to be X11, well, you can go find X12 and then replace it with X11 and then you're all done. It's a really nice troubleshooting tool and it's a nice fixing tool as well. So we already talked a little bit about the memory monitor, so I won't talk too long on this, but just to reference, these are the bits, these are the individual bits, and on the right side, you can click this little field right here, and then you can input 1, 2, 3, 4. It will fire the respective bits, or you can change the bits individually. And then on the right side, you'll see that we have the hexadecimal and the ASCII value for your reference and your ease of access. So this is what I was talking about earlier, the online edit. So this person, whoever's using this program, is online with the program right now. They clicked the mining tool, they came in here, they added a row, and then they need to add some logic here. And then when they add the logic, they'll be able to use this little save tool. So I'll go ahead and showcase that real quick. So let's go ahead and link download and monitor. Should just go ahead and work. I know I have no logic, but as long as you have an end instruction, you should be good to just test out this feature. So I am now online with my PLC simulator. So if I do an online edit, it will put me into an editing mode. The screen kind of turns like a green color. I can edit a rung. I can add like F10, which is an always on bit. Really cool bit to memorize is F10 bit. And then I can have that go to Y10, another bit. And then when I'm done, I can have that save. So this is now part of the program and I didn't even have to go offline. So pretty cool stuff. I'm gonna go ahead and disconnect, but just wanted to showcase that real quick. All right, we're gonna jump into part 5. Any questions before I move on? Nope, okay. So we talked a little bit about the comparators earlier, how they're word comparisons. So this is the arithmetic comparators that we do have. We have equal to, we have less than or equal to, we have greater than or equal to. We have everything but this number. So everything, like if you had, it's less than or greater than, so everything but that number. We have less than, we have greater than. Basic operators, but we do host them. We have add, subtract, multiply, divide. Recommend that when you do multiply and divide that you allocate 2 words open for the operation. So when you're when you're programming your project, make sure that you take into account that you're probably gonna have to use 2 words for a multiply or divide operation, especially because the divide will take into account the whole floating, the string that, or the string of characters that come out after the division. When we look at other operations, we have some cool ones like move, MC, increase, decrease. So we can move bits, we can move words, we can move double words. So you would use bmove or bitmove for moving bits. You would use move to move words, and then you could use dmove, so double word move, as we talked earlier, to move 2 words at once. We have an MC, which I will highlight in a program later. But this will allow for certain parts of a ladder diagram to not operate until it's been activated. So this is a pretty cool command because the MC is looking for the MCR command, and anything in between will not operate until MC has been energized, outputted. And then we have increase and decrease. So we've used this a little bit in the prior slides, that when the rung is activated, that it will increase device D by 1 every scan, and likewise with decrease, it will decrease by 1 every scan. We have date read. So to get to the PLC time clock, we have to go to PLC status. We have to set the PLC time, and then when we do date read, so this instruction right here, you're going to be reading the date from the F30 register. I believe it was F30 or F40. We can look real quick. F40. Okay, so it was F40. So F40 to F43, this is the date read. So it doesn't look nice straight out the gate, but this is referring to the year right here. This is referring to the day, or this is referring to the hour, and then, or the day, or the month, then the day of the week, then the hour, the minute, then the second. It's all in hexadecimal. The way to make this look nice is just to use the instruction. So I can come in over here, and then we can do an F10 bit, and then we'll do date read F40. Why is it not? Oh, I'm sorry. It shoots it to the destination. It already reads F40 for you. So if we do, let's just do D0, it will put from D0 all the way up to D7. I believe it will put in the different parameters for each, and we'll go through those. So I'll go ahead and save that. And then we'll go to the memory monitor. And then when I go to the D device, so it's the year 2020, June 15th, 9/11, and then here's the seconds, and then it's the first, or day 1. So day 0 would be Sunday, day 1 is Monday, all the way up to day 6 being Saturday. So then that's how that works. And then likewise, you can do date write. You can take a date from one of your devices, or you can write something onto another device. It will write it from certain device to the actual PLC itself. So we talked a little about this before. It's the timer on. So the TON function, when this is on, it will start counting T1 up to 50. So this will be 5 seconds, because 50 times 100 is 5,000, 5 seconds. After 5 seconds, T1 will be energized because it's been reached, and then M30 will become energized in response to that as well. Timer off. So when M40 is off for 5 seconds, T2 will become energized. So this is a different way to look at timing. You can just do it the opposite way. So as long as M40 is on, this timer will not count up to 50. So we have counter up and we have counter down. Let's cover counter up. So when M100 is turned on, so a 1, it will count C1 up to 10. And when C1 reaches 10, it will become energized itself, within the ladder logic, it'll be producing a 1. Let me go ahead and exit my Cimon software real quick. And then if we want to reset the count, we just activate M101, and then this will reset it all the way back to 0. And then this is displayed in this graph down here for future reference. So just like counter up, we have the counter down. So it starts at 5 and then it counts to 0. When it hits 0, C2 becomes energized. And if we want to reset the count back up to 5, we would just turn on M111. So these are bits, just as a reminder. And this is a bit, not a word. So it's referring to word 12, bit 0. So this is the ladder logic that we'll be going over. This is a little fun project that I created for us to look through. This is going to be creating a water tank, or it's going to be taking control of a water tank, filling and draining it, manually resetting it, and starting and stopping it. So let's just go through it ladder or row by row. As you can see up here, I've named my bits some little names here, variables to remind myself what they do. So this M01 bit is resetting the whole tank. So I know that when I look at this later, I'll be like, oh, M01, that resets, or X00, that starts and stops the whole process. So when I want to reset, I activate this bit right here, and it will move a 0 into the tank level M100. So this is essentially resetting the whole operation. If I want to start and stop my draining and filling, I can activate X00, and then this will activate that MC command that we were talking about. So MC0 is looking for MCR0. If I come all the way down here, I see MCR0 down here. So all of this logic in the middle will not activate until this bit right here has been activated itself. So it's a master control run. So when we go to the next row, we'll see some F92 bits. So these are clocks. These are internal clocks. As a reminder, F is for reading only. So F92 is it's on for 0.1 seconds, and then it's off for 0.1 seconds. And then notice that these are also one shots. So Y10 is off by itself by default. So that means that this is always adding 2 to M100. 2 plus M100 equals M100. So it's just adding 2 to itself consecutively. But at the same time, it's also subtracting 1. So in essence, it's only adding 1 to itself every scan. And then after that logic's been computed, it will reset my reset, because I don't want it to just stay on. I just want to be able to press a button and then it resets itself, so that I can daisy chain in a sense. I can have access to that reset as well by just attaching it to this command up here. I could have also done that up here. It doesn't matter, but I just chose to put it right here. And then I have parameters for when it will fill and when it will drain by itself. So when the tank level is greater than M50, it will activate Y10. When Y10 has been activated, this will no longer be turned off. So this will be a 1. And then this will no longer add. So we'll just be subtracting 1 from the tank level every scan until we reach this parameter down here. When it has reached less than 1, it will reset Y10. Therefore, I will be adding 2 again. So we'll be adding 1 to the tank level every scan. Now, at the beginning of the scan, I have an F12 bit. So this is like cold initialization in practice on at the first scan only. So this F12 bit is pushing a 99 into the D register, or the M register M50 for me, which is my comparator right here. So when M100 is greater than M50, I could have also put a 99 here. But if someone else was using it and say they wanted to put like a 40 in M50, they could do that from the HMI or the SCADA. This is just for the default process. A 99 would be there. You could change that later, because this is only on at the first scan only. This is the tank that we'll be working with. This is the SCADA software. I'll be showcasing this more in detail on Wednesday, but for right now, I know it says HMI, but it's going to be the SCADA software for this demo. So if I go, let's close this project. And then I think I'm offline, yes. We still have the simulator up, okay. So recent project, I'm gonna go ahead and connect to this project right here, which will have all that logic we were just talking about. I'm gonna delete this program from the project. So the only real difference is this M00 on the the slide I just showed you is X00. That's a physical input. So M00, if we remember, is a virtual memory bit. So we can use that as a virtual memory bit or a virtual input. So I'm going to have this download and monitor to the simulator. And then I'm going to open up SCADA on the other side. And I will be giving these projects out to you guys so you can mess around with them as well. So don't feel like you're being left behind. So I'm going to search and open. Oops. So this is the little tank. We will be going more over this on Wednesday. We'll creating a whole project just to kind of preface what you guys are going to be looking at. Like all these sheets we will be going through on Wednesday, so don't worry about that. I'm going to go ahead and start this. You haven't missed anything with SCADA is what I'm talking about. So I'm going to go to alarms, log in. All right, so this is that slide that we were just looking at, and in reference to this over here, it has to start first. So right now, the simulator is talking to the SCADA. If you want more introduction on how to get this started, I can show you. I will be showing this on Wednesday though. So this is the on and off. This is controlling that M00 bit. So when I press this, the tank level will start rising. And as you can see, I did activate that bit over here, and now logic is actually computing over here. I can also turn it off, and then it will stop because the master control is not on anymore. So therefore, everything has stopped. So you can test this out without actually owning any hardware. You can use our 4-hour software license as well to talk to our simulator. And if you ever get a physical HMI, you can do a physical HMI talking to our Cimon simulator as well. And then you can also data throughput the Cimon simulator with the SCADA talking to the physical HMI. So there's a lot of versatility in terms of not actually owning the hardware, where you can talk between devices and just test them out before you get them. So I'm going to go ahead and I'm just going to go ahead and start this again, let the logic go to itself, or let the logic build on itself. Once it hits 100, remember it's going to drop back down because it's over 99. And then we have an indicator light right here that's showing that it's draining. If I wanted to manually reset it, I can just press this button right here. It will put it to 0 automatically, and then it will continue its automatic process. If I wanted to drain manually, I can click the drain button, which also acts as an indicator light, as I said, and then go down to 0. If you wanted to stop draining, you can turn it off, turn it back on, and then it will continue to fill up again on its own. Go ahead and disconnect from everything. And any questions before I move on? That was quite a lot of information to throw at you guys. No questions? Okay, and everyone's following along. Everyone can see my screen and hear me. All right? Okay, I'm just going to continue. So we have the PLC setting application for part 6 to go through. So out of basics, when we go to the PLC parameter, which is located in your project tree, if I go down to PLC parameter, double click here on the basic, I can see that's where I'm setting up my timers. So T0 through T127 counts up 1 for every 100 milliseconds that goes by. So that's when I saw T0, like when I saw this operation right here. So we know T1 counts 100 milliseconds per tick. So I'm just taking the 100 that's embedded for T1 and multiplying it by 50, and that's my second counter. So 100 times 50 is 5,000. So altogether, this is a 5,000 millisecond counter, or a 5-second counter.
Christian, can you specify the scan time, or is it something that's set by the particular PLC?
It's something that's set by the PLC. So depending on how long your project is would determine how long the scan is.
Okay.
So a shorter project, yeah, I hope that makes sense. A shorter project would be a shorter scan time. A larger project would be a larger scan time. It does scan each individual program though. So when I mean programs, right, like these programs in the project tree, it scans each program with its respective time. So for the XP, it was 75 nanoseconds. For the CP, it's 200 nanoseconds. And then off the top of my head, I don't know the PLCS, but yes, it spends that amount of time. And that's by default. You can't change that per program. But you can see how long it's taking the scan per program in PLC status. So if I go online, or if I go to, it is online, but what was wrong? Why can't I? Oh, I have to connect. My bad. All right, if I go online, then I go to PLC status, I can look at my scan time down here. It will tell me how long it is taking to scan the program each time. So the simulator is taking 15 milliseconds per scan to actually do all this. Okay, so this is where we can set up our timer. So T0 through T127 does it by 100 milliseconds. It counts up by 100 milliseconds per tick. And then T128 to 4095 counts by up by 1 for every 10 milliseconds. So you can choose between those two. There are some other parameters here to look at. Nothing too fancy, just expansion, hot restart if you need all that. Latch reset area, or latch area, is where we use our K. So K, if you remember, I said it was for latching device registers. This is where you would set that up. You could use M, L, all of these different devices to be stored inside the K in terms, or in case that something would ever happen to your PLC or you went down for a little while, all your volatile data is being stored. And then we talked a little bit about periodic interrupts. This is where you would finalize the setup of that program. So the interrupt here is a priority level 0, and then it's an interval of every 10 milliseconds this interrupt is happening. You would double click here to see what the program is actually committing to. So if you deem that an error is okay, that an error will not hurt someone, you can always bypass those errors. And you can do so here in the PLC parameter, so you can keep the PLC running if one of the modules has failed, if a from-to error occurs. If any of these errors occur, you can keep it going through that error by coming here and then checkboxing one of these boxes. Otherwise, I would be very careful on how you use these boxes. Here's our COM port parameter setup. So you declare the station number, the type of communication, RS-232, 485, 422. This is for serial communication COM port. And then the baud rate, making sure that all of these match specifically to what the device you're talking to in terms of baud rate parity and all that fun stuff. And then this is where we do our Modbus slave setting. If you're going to do Modbus master, that is part of the actual making a program. So if I right click on program, new program, you'll see I have master Modbus right here for serial, and then you'll see I have Modbus master for TCP right here. So this is where you do master for Modbus, and then slave is done in PLC parameter. So you're just setting up the device registers and then the station number accordingly. So when we're in the reserved I/O, I kind of showcased this earlier. I wanted to demonstrate how devices are being allocated their memory and whatnot. I gave one of them 0 points, 16 points, 32 points, and 64 points. Just wanted to refresh you guys' memory that we do have this capability in case you do need it. It's there. But typically, all in all, your Cycon will auto-detect what devices you're already talking to. So some competitors, you have to declare what modules you're talking to. With ours, as long as you have them hooked into the chassis or into the PLCS, once you connect to the PLCS or the XP to CP, it will auto detect the rest of the modules. It's really nice stuff. Any questions before I move into part 7 for communication? Okay, so for part 7 communication, this is asked a little bit, do we cover field bus? And yes, we do, but the field bus is not embedded internally for the PLCS. That is something you would have to get another module for, or you would have to talk through the HMI. And I recommend talking through the HMI because the HMI has so many open protocol. It has so many protocols in general to talk with that we'll cover those tomorrow, but it's just a lot cleaner when you talk through the HMI. As you can see here, the Ethernet protocol and the serial protocol, that is for talking to our own devices. This is not like this is not an Allen Bradley. This is not to be confused with Ethernet IP talking to Allen Bradley. If you're going to do that, you would have to talk to our HMI or our SCADA, and then in return, you would use one of those to talk to an Allen Bradley or Siemens. All in all, you could use one of our HMIs or SCADA to actually bridge connections between a Siemens and an Allen Bradley PLC, or Mitsubishi and Allen Bradley, what have you. You can also use our HMI or SCADA as like data throughput from one device to another. It's really nice stuff. So moving on through communications, this is what the Ethernet loader or the Ethernet protocol looks like. You can make your own frames. You can make your own error checking codes. You can treat it to be UDP or TCP. The COM result will always be stored wherever you want it to, but by default, it's usually an L device. We typically use our L devices for the COM result. So try not to overlap those because there will be communication conflictions. Yes, continuing on. This is the rest of the packet formatting, the frame settings. You can have whatever segments you want to use, don't care, link device constant, and then the famous BCC error checking. I would not use CRC as we do not support that. I'm talking about your device that you have on your side. In the future, in the very soon future, we will have CRC error checking, but for the time being, I recommend just sticking with BCC. Any questions before I move on to part 8, which is analog? We're going to be moving a lot quicker right now because we're just going to cover a little tiny technical details. All right, for part 8, we're going to cover analog modules. These are the different types of modules that we have for the CM1 series. We do have analog modules for the CM3 series. 4 channels input, 4 channels output, and then a 2-channel input, 2-channel output for the PLCS. But when we're talking about the CM1 series over here, we have a 4-channel analog to digital, which is the current or voltage. So V standing for voltage, I standing for current. We have an 8-channel voltage, 8-channel current, and then a 16-channel voltage or current. And this is analog to digital, A to D. So this is kind of what the wiring looks like when you have A to D. So if you're dealing with both voltage and current, you would want to get like this type of module that has both of them. Or if you wanted to measure how much current is in one of your voltage readings, you can also use a setup like this. So you can have everything coming into the voltage reading, and then there's an embedded resistor that if you connect a wire from that pole to this pole over here, it will be able to understand the amount of ampage that is going through that voltage. So in essence, you can get the amp value from whatever voltage you're reading. Or if you're not going to be dealing with amps at all, you can just strictly stay with the voltage type of module, or you can stay with just the current module if you want as well. A little bit about the setup. So like I said, when you have the module set up with your PLC, when you've inserted it into your chassis or you've hooked it up to your PLCS, Cimon software will automatically detect that. Once you're online, you can double left click on the module, and then you'll get a configuration window that looks like this. Then you're going to click on the channel that you want to set up. So this person's wanting to set up channel 2. So they click on channel 2, they press setup, then they start going through the different little parameters to set up. So the input type, they've chosen 4 to 20 milliamps. It looks like they're going to disable it right here, but this is just showing the different examples that we have. So 4 to 20, 0 to 20. I recommend staying away from 0, because if you do choose 0, it's really hard to troubleshoot, because if it's off, it's going to be 0. If it's not working, it's going to be 0, and it's really hard to distinguish the two. If you choose 4 to 20, when it's off, it'll be 0, and you know it's off. Or and when it's on, it should always be a bare minimum of 4. If it's on and it's a 0, you know something's wrong because it's not 4 being the minimum. So I recommend staying away from 0 being your lowest point, but that is completely up to you. And then we have signal processing, which we can do average by samples time, or you can disable that. and then you can change your digital value range. If you want to be more specific and not lose any data registers, you can choose the more precise values for your bit ranges, or you can do the clean bit ranges. So as here we see -192 to 16191, or you can choose 0 to 16,000, or you can choose the cleaner one for the 8,000 range as well. And then once all of that is said and done, you will have set up your channel 2 for your analog to digital module. Now you want it to read and write data. Typically you would want to read data coming into an analog to digital module. So you would press read, and then we can view what data is being read at that specific moment in time. And then we can reset the min and max, and we can reset an error if an error did occur. But make sure you deem it very safe before you reset an error. Now, I've been talking about this for a while now, the from to commands, because we're talking about buffer memory or user memory addresses, and you're talking to I/O cards in general. So I/O cards have their own I/O addresses, so because they commit to actions outside, but I wanted to talk about the from to command. So let's dissect this real quick. So if M50 is on, this will execute. So this is a from command, meaning it's taking data from the buffer memory and storing it into the CPU. So this is memory that's being stored in the I/O card itself. So a little bit about the notation. This is referring to the expansion number and the slot number. So over here, as we can see, it's in hexadecimal. So there's not decimal values. It will always be a 0 in the first component of the 2-digit number. So it'll be, and here we are talking about expansion 0, slot number 1. So slot number 1 is not the first one in line, that would be slot 0. So the slot 1 is actually referring to this one right here. I know that there's a dotted line right here, but this is where slot 1 actually is. When we talk about the buffer memory number 2 component, when you go to the help file, or you should get a list of instructions with each module that you buy. This is the buffer memory address. This is referring to the actual decimal value, not the hexadecimal value, but the decimal value. So buffer memory number 11, they're wanting the digital output value of channel 1, and they're going to store that value to device register D1. So as remember, that's word data register, and then it's going to transfer 1 word of data. If we had a 2 right here, we would want to make sure that we don't touch D2 with anything else, because it's going to send 1 word to D1, and then it's going to send another word to D2 consecutively, depending on how many number or what number that we put here for number 4. So just to recap, it's going to take buffer memory 11, so channel 1. It's going to, from expansion 0, slot 1, and it will in turn put that data into the CPU and at location D1 in a total of 1 word of data. And likewise, we can use a to command to send data from the CPU all the way to the I/O module, and then overwrite whatever data is in there already. Any questions on from to command before I go into part 9? Convenient functions. We have about 24 minutes left with today, so you're welcome to ask questions, what have you. I'm going to jump into part 9 though. Looks like no one has questions. So when we look at the PLC simulator without having to buy hardware, we could set up our own little virtual chassis and see how things would work. Down here at the bottom right, you'll see it is showing the I/O addresses per card, or for this card right here, the DA8 channel card, and then it's showing the I/O, and then it's also on the right side is showing the buffer memory. So the decimal number over here is what you would refer to when you're looking at the buffer memory. Another way to see the buffer memory. So if I wanted to see, where's the name of that card again? Let's see. Let's look at CM1 AD. All right. So if we go to the help manual, main help, if I go to contents, let's just open up the CM1 right here. And then I'm going to go to AD converters. And then I'm going to go to the buffer memory. And then I can look at, this is what the buffer memory of any of the AD cards look like for up to 18 channels. If you step into the 16 channel or 8 channel VI, this is where you would look right here in parentheses, you see this. But this is the buffer memory. There is one of these charts per module, so you're never alone in trying to guess. and you don't have to actually use the Cimon simulator to see it. This is more so just to test out hardware before you even buying it. So to use this, in essence, you have to actually turn it off. By default, it will be on. So what I mean by that is if I go to Cimon, I'm here, I have to disconnect, I am disconnected. So it's on already, I have to turn it off, and now it is actually on, or it's actually off, so I can actually mess around with the chassis. I can choose one of these CPUs, I can, so the PLCS by default can only have 12 slots, that's why it's not letting me choose the slots, but I can choose a card if I want. So I come here, pick a power card, or an IO card, or I can pick another special card, and then when I click on that, press OK, it fills that card right there, and then I can look at the IO, and I can look at the buffer memory, what actual values are being used within my logic. All right, let me just, I was disconnected, okay, good. We do have this cool little feature called cross-reference, so this helps out with troubleshooting. So say you used a bunch of X12s or C13s, what have you, whatever data register you're honestly looking for, you can come into Tools, go to Cross-Reference, and then click on the variable that you're looking for, and then look for that number, and it will tell you what step it's being used, what instruction it was being used, the start, the end, the variable, the description. Very good troubleshooting feature if you do have something going wrong with your project. So that is located Tool, then Cross-Reference right here. It's a little scissors looking symbol, or an inverse forward sign, if you will. It looks like scissors for me. Now, just jumping back into permission mode, after you've created your project, you don't want anyone touching your project, you've created a backup project in case you forgot your password or something like that happens. You can always go back into the project details and then change the security settings to actually incorporate a password. The way to do that is to go to File, then you could go to Project Properties, and then this is where you would do security settings. Or you can right click on Program and then go to Set Programming Editing Permissions. As we talked about earlier, we talked about the PLC status. So if something's going wrong with your PLC, it will show up here in the PLC error message window. It will usually give you an error code, and then you could in return try to locate that error code in the help manual, or you could contact us and then we can investigate that further for you. Our hardware does have a 2-year warranty, so they last pretty long. There shouldn't be any errors up until that point, but if you do encounter errors, we're always here to help you. I don't want to advocate that we get errors very often. We don't, but if you do, it's there to help. We have the firmware versions, like I talked about, that you can upgrade for free and revert down if you need to as well. There's a PLC diagnosis. This will tell you if the card is being detected or not within the chassis. You could also look at the bottom left hand corner right here. If the card is not active or it's not being picked up, it'll just say no card right here. So that's a similar feature to what's going on right here. And it will also tell you if it's running out of data or if it's clean, what have you. In the future, we will be having a feature called PLC Doctor. So it will be able to tell you if your IO, your digital input, output, or your analog input and output is off by a millisecond in terms of reading. So it was used to reading every 10 milliseconds, but now it's reading every 11 milliseconds, what have you. It will be able to tell you that it's getting off by a 1 millisecond. As any type of technology occurs, it always breaks down over time. It gets slower because of friction. There's constant friction going back and forth with communication. So it's there to help you in the future, PLC Doctor. It'll be released with our Linux-based PLCs. So a nice little feature, if you don't want to look at the memory monitor, you just want to look at the devices that you used, you can go to View, Device Monitoring, and then when you click Scan, it will scan all your projects and then input all the data registers that you use, so you can only look at those, so you don't have to look at a giant memory monitor the whole time. So if I go to Device Monitoring, which is different, I can delete all. and then all I have to do is press scan, and then it will scan this program, my whole project, and it will tell me which devices I'm using, the descriptions, and their values in real time. But I'm not connected to my simulator right now, so nothing's going on. And then we also have device trend. This is not historic, or it is historical to a point. It's historical while you're connected to your PLC. Once you disconnect, it loses all of its data. It's not like an HMI or a SCADA software trend graph. You would not want to use this as a historical way of measuring your devices. This is to look at values in real time to see if they're acting appropriately to what you expected. So this is just an extra step on top of other things to verify that your program is working effectively. So the way to get here would be go Tool, Device Trend, and then you could do right-click, Insert, and then this is where you would insert your device that you want to monitor over a given amount of time. Make sure you change your max value accordingly, and then once you've done that, you're good to go. It will just start recording the data. Once you disconnect from your PLC, it will no longer show those values anymore. You will lose the whole trend graph. You can take a print screen if you want. That's fun. So this is one of the last slides. This is talking about our F flag. So I wanted to showcase this a little bit, then I'll go into the actual Cicon and show the Fs a little bit more. But these are your read-only registers. They have already embedded committed functions that you would want to use, like run mode. If we look right here, F10 is always on. We did use this in my program. And then there's the F90s, which were embedded clock functions. And then F40 for our real-time clock. That doesn't show right here because it's referring to the bit words. But F40, if we remember when we did date read, grabbed the real-time clock for us. So if I go in here, and then I go to the variable window, I go to the F bit, I can scroll down through the description and it will tell me what it's being used for. And just because every bit is not being used doesn't mean that it's not being used within a word. So sometimes the words are actually utilizing those bits collectively inside one word. So it'll tell you the status of your base. You can look at the status of, oh, it's not scrolling anywhere. Sorry, 1 second. Okay, cool. So you can look at the status, you can look at the error codes. One of my favorite are is bit 34. So this one will tell you if your battery is low. So I mean, it wouldn't happen right away, but it might happen like 2 years, 3 years down the road. Your battery might become low. You just replace it. And then if I go all the way to the 90s, which are my favorite, we'll have some embedded clock functions. So you don't have to make your own counters or timers. So what this is saying is this will be on for 0.01 seconds, so 10 milliseconds, and then it will be off for 10 milliseconds. This will be on for 100 milliseconds, or yeah, this will be on for 100 milliseconds or 50 milliseconds, and then it'll be off for 50 milliseconds. So just cut the number in half. That's how long it'll be on. That's how long it'll be off. So this will be on for 30, or yeah, this will be on for 30 seconds, then it'll be off, or, oh my gosh, I'm losing it. It'll be on for 0.5 seconds, then it'll be off for 0.5 seconds, and then so forth, off for 1, on for 1, and then off for 5, on for 5, so forth, all the way up to a minute. Anything past a minute, you would want to create your own, and it's easy setup. If you need help setting up a clock that is on for like 5 minutes and off for 5 minutes, I can help you do that. It's not a big deal. And I think that about covers everything else. Thank you for showing up today. I will be taking questions. I'll be leaving this room open until 10, where I will be turning it off, and then I'll be sending out projects to you guys. I'll be sending out the presentation you just witnessed, and then I'll be sending out the recording for your viewing pleasure as well. But for right now, you can ask questions, or we can just dive into this Cicon software if you want to see me do some more stuff, what have you.
I got a quick question. If you create a FBD in a project you're working on, is there any way you can store that in like a global way so you can use it in different projects?
Variable frequency driver? FVD?
I'm sorry?
Did you say FVD? Variable you didn't say VFD, right? Variable frequency driver?
No, like a function like a special function, subroutine, or I think you called it.
Oh, subroutine? Yeah, so if you do a subroutine, let me come over here real quick. So if I go over here, new program, you click a subroutine, it's going to overwrite. So I have a subroutine program right here. If I come to my main program, I use a special function called eCall. And then it will call out to the certain subroutine, go ahead and run that subroutine, and then it will come back and scan the rest of the program that called to it in the first place. So you identify it with its program identifier, and then the N referring to how many programs or how many subroutines or how long. Sorry. Did that answer your question?
I'm sorry, I was actually talking about a function block diagram, or like
Oh,
say
the function
you in the
block
bottom
diagram.
left
Yeah.
that you get the user library.
Yeah, you have your user library. You can just click over here. So like we're in the CM3 series. So if I believe it's just I can click and drag it and then embed it, open it up, and then start looking at how it functions. And then I can input the devices per parameter within the function block itself.
How do you make your own? Is it possible to make your own? You have to use the.
Oh yeah, you can make your own. Hold on. Use customize. Hold on one second. Yeah, so add FB. So if you right click on the user library, your own library. So if I add FB and then I can name it, password confirm, I believe I press OK. And then, yeah, so, and then once you'll have a variable or a program function block, and then you can just start adding your input, adding your outputs, add IO together, the type. You can manipulate this based on however you want to do, right? So something like that. And then, yeah. Does that better answer your question, how to make your own?
Yes, and is that something you can use, say, if you close down this project and open up a new one? Is that still there
Yeah,
available?
it will save to your user library within this one. So when you open up the other project, you would want to, so it's going to ask you to import, I believe. Let me see. So you can import the FB library from a different project. So then you're going to have to go into that actual project folder, and then you're going to have to go into the upload, I believe, and then you would pick it here. I have never actually used this feature, but I know it's there to be utilized. So if you really want me to show you, I mean, we can go through it at a later time, but I know that the capability is definitely there. So once you create this and you go to a new project, when you're in that other new project, you come here, right click on your user library, import the function block library, and then go to that project you were talking about. And then there should be a file there for you that you can incorporate into this new one. Does that make sense?
Yes.
Okay. Yeah, you're never alone when you're doing these. It's not finding them right now because we haven't created them. But yes. I think someone else had a question. Hold on. Two people had a question. Thank you, sir. Yes, let's look onto the Cimon software. Okay. Yeah, go ahead and ask your questions, Sri. Oops, everyone. What is your question about? Got about 8 more minutes to get your questions out if you do have some, guys.
Is the default action to go to stop mode if you run over your like a scan time? Is there like a watchdog timer?
Yes, that's found in PLC status. So, or PLC parameter. Sorry, I misspoke. We go to PLC parameter. We have a watchdog right here, so you can enable it for however long you need to set it for. I'm guessing the minimum would be 1 millisecond. So this is that watchdog timer you're referring to. So the communication for Ethernet is just between our devices, sending certain packets of information between our devices. If you're wanting to connect, so depending on what type of driver, so that's the SCADA, that's not really our Cimon software. But if you're wanting to connect with Cimon, so when I'm inside the SCADA software here, if I go to IO devices right here, this is my simulator. So I'm going to add a station, or actually, let me go to, I think this is a better way. Okay, so I'm going to go to a new device right here. And then these are all the native drivers that come with our SCADA software. You'll find the same list with the HMI as well. So if you say you're doing, let's just do a very broad example. Let's do Modbus. So I have Modbus right here. 1, 2, 3, 4. I'm just gonna name it Modbus TCP. Press OK. Add station. Well, let's name it a sensor. It's Modbus TCP. Has a station number of 1. I need to know the IP address. So 192.168.0.45. Let's just say it's on that address. And then the scan time, the timeout. Press OK. Now you're not done, because you need to add some COM blocks for the Modbus. You know your registers, so the block number is not necessarily important, but for the address, so we know we talk to the 0, 1, 3, and 4 addresses. So those are the only addresses that we talk to in terms of Modbus. But then you come over here and just type in a 0, and then it's the first 20 words. So it'll do from 0, 0, 0, 0, 0 all the way up to quadruple 0 or 000 20. So it'll just do the first 20 word, or 00019. It'll do the first 20 words of this register. So since we're referring to 0 and 1, those are only the bits, but we'll consider those words when we're talking about Modbus. If I actually wanted to talk to the word registers, I'd pick 3 and 4, obviously, and press 0. What is going on? No, it wants me to actually type out the full 4 zeros. What's going on? Huh. Okay. 1 second, sorry. Why am I getting an invalid address? Excuse me, I'm trying to troubleshoot my own failure right now. Oh my gosh, I'm so dumb. There we go, because it starts at 1, not 0. Duh. So if I wanted to add more COM blocks, just do the same thing. It's 20 max per COM block, but you could go up to however many you need. So I'm going to change it over to 1 now, and then I'm going to go up to 3. And the same thing, rinse and repeat all the way up to 4. So now I'm talking to all these Modbus registers through my SCADA software, and then I have to put in the IP address of the actual computer itself. So if you go to command, you go to IP config 1222. I know that I put the IP address of 0. Whatever in the other one, 0.4445. We can just change that real quick. It's not a big deal. Obviously, I would want to be on the same network. So press OK, come here to save. So then now everything is set up. I can talk to the Modbus TCP. So now this is Ethernet communication going to your field device. And then in return, you're going to want to talk to your PLC, right? So then you come new device, you can choose Cimon PLC Ethernet, so PLCS, press OK, add station, choose the PLCS over here, PLCS again. You're going to want to put the IP address of that PLCS, so 192.168.0.1. Let's do 50. That's what the PLCS IP would be if we were, this is just hypothetically speaking. Press OK, add COM blocks. We were talking about X, Y, M, and Z, or Y or D registers, so let's just do some of those real quick. So 50 words of X, just type in 00 to add for the COM block. This is something you would not have to do on the HMI, just letting you guys know. This is just for the SCADA server or the SCADA software. And then let's put an M as well. So now I can talk to these registers within the PLCS. The group number actually doesn't matter. This allows you to actually, for the SCADA to recognize those registers coming from the PLCS. We're not done yet. We have to go to the COM port. Come to the COM port. We have to identify our or our SCADA software. I know it's this one just because of my laptop. That's just how it is. But typically on yours, when you set it up on your computer, it will be the first one here, and it will be the IP address that you see right here. Mine's a loopback, so it's just a non-functioning IP right now. I know it's this one, but this is how I would set it up. I press save, close. So currently, the SCADA software is bridging communication between the PLCS or the PLCS and the sensor device, or you can have it just talk through Modbus through the PLC to the actual sensor device. The way to do that would be to come to the Cimon software, new program, Modbus TCP master, press OK, and you'll get a program like this. So where is the slot? And if you don't, to remind you guys, you can't use the PLCS CPU as a Modbus master. So you would have to get a dedicated Ethernet module. So let's just say we put the Ethernet module at slot 3. If you ever forget what slot your card is at, if you double click on it over here in the chassis, it will tell you what slot it is when you open it up. So that's just for your reference. You go here, press new to add the IP address of the sensor that you're talking to. So we said it was 192.168.1.45, and then don't change the port number. The status code device will be here. And then this is where you would start adding in, like, where is this thing going to be talking to? So the Modbus devices, station number 1, let's say, it's talking to the 0 registers, so the 0 coils, the start address, so 00001, the data size 1 bit, and then this is where it's recording that result. It's recording it to M00. So M00 is where 001 will be recorded to. So let me write that on Notepad real quick. So sensor is talking through Modbus to the PLC, and then the PLC is taking, let's just say Modbus register 1 to the PLC, and then the PLC is using a send or receive command to target this function right here, and it's taking Modbus register 0001 and then inputting it into M000. So the sensor, and all you have to do is essentially make a Modbus master program, tell the data register for Modbus to be pointed at a device register within PLC. It looks a little bit complicated, but it's really not. Okay. It can be 5 zeros or 4 zeros. Our program will adjust accordingly. So I know if you go to our PLC parameter and you go to the Modbus slave setting, you'll see a bunch of zeros. Typically, it's not this many zeros. We see 5 here, but it can also be 4. So it's either or. We support 4 or 5 zeros. Does that help answer your question, Sri? And I know you said thank you for explaining. That's great. I just wanted to make sure I answered that question. Okay, cool. Any other questions, or I'll just be wrapping up today's lesson. I'll send out the projects, the recording, and the presentation. All right, I'll take that as a no. Thank you guys so much for showing up today. If you have any feedback, feel free to send me an email, something that maybe I could do better, or I would love to improve this type of training for everyone. I try to take people that have had no experience with PLC and even veterans in this field and just bring them up to speed with maybe new things they haven't seen yet, or just, you know, highlight a couple things here and there. I'm really trying to make this a versatile type of lesson, like a one size fits all kind of lesson. So if you have any room for improvement to add for me, that would be nice. I love constructive criticism. Otherwise, have a great day, guys, and I'll see you tomorrow at the same time for HMIs.